So today we are going to continue from where we left from, and this is on that topic, which is oscillators. So an oscillator is a device that produces an output without an input, and it's not only required that it just gets powered. Once it gets powered, then it's going to give us whatever we refer to as an output waveform. So this is a device. That produces an output waveform without an input. So long as the device is powered. So there's a difference between an oscillator and a waveform. So you can have the differences between oscillators and waveforms and amplifiers. Differences between oscillators and amplifiers. So you can have our table here. This is an oscillator, and this is an amplifier. So this is the first difference is that it's a two-terminal device. Is a three-terminal device. What I mean by two-terminal device is that an oscillator will look like this. This is an output, this is power. Whatever we mean by the three-terminal device is to appear like this. This is the input signal. This is the power. And this is the output signal. So that's the first difference. Then go to second difference and third. So this is what I mean by the two-terminal device and the three-terminal device. The second difference is that when you look at this, an oscillator has no input. They do not have inputs. Here is that they have inputs. That gives us the second difference. The third difference is that when you look at the oscillator, it's basically an inverter. And we look at the amplifier. This is basically a converter. Converter means it's changing energy from one form to another, but not in. It's basically converter. So this is these are the difference between the oscillators and amplifier. So we're going to do on something on the concept of oscillation. Concept of oscillation. More oscillators. We shall have a circuit to describe this. There is a switch. This is a power supply. And this is a resistor. This is a double pole or bipole. This is a capacitor. This is an inductor. So this is the circuit we are going to use to describe the concept of oscillation. One of which is that for us to first generate the oscillations, then we must be able to charge a capacitor, then disconnect the charging circuit and connect the charged voltage across the capacitor to the inductor. So the first thing we do, we are going to have, we close the switch. When we close the switch, then we shall have complete the circuit all the way to the capacitor. And after that, we are going to have a situation whereby the capacitor is going to charge the maximum supply voltage, after which, when the maximum voltage is achieved, then we are able to disconnect the switch. When disconnect the switch and move the bipole switch to terminal B, then the energy stored by the capacitor will be made to start discharging. The electrostatic charge will now decompose to electric field. When the electric field now, then the inductor will charge. And because this charge is such that it's transient, the inductor will also be able to store charge. So this circuit will keep on charging and discharging within each cycle. And at the end of the day, we shall be having what I refer to as oscillations. We shall be having what I refer to as oscillations that are 2 and 4. So when we are asked to explain the concept of oscillation, then we need to know that the first thing is that we need to understand the diagram first. So initially, the capacitor is charged to maximum supply voltage. Through the resistor connected in the circuit by closing the switch and connecting the bipole switch to terminal A. Once we know that, then we shall charge the capacitor to maximum. The bipole switch is then moved to terminal B so that the electrostatic energy, stored by
the capacitor is discharged through the inductor. Discharged through the inductor. Full stop. Then therefore, a magnetic field is established. Therefore, an electric field, not magnetic, an electric field is established. Therefore, an electric field is established around the inductor, and so the inductor is charged to maximum energy stored by the capacitor while the capacitor discharges to minimum or zero potential. So once the capacitor is fully discharged, the magnetic field established around the coil collapses and charges the capacitor again to maximum energy or voltage supply. So this process is repeated is repeated to and fro the inductor and capacitor. And as a result, oscillations are generated. So once you know how the circuit works, we're now going to be able to describe with actually the types of oscillations we have. The type of oscillations. So there are two types of oscillations. We have the damped oscillations The damped oscillations are the ones that are able to die with time, or they're able to see their existence ceases with time. And therefore, they move from the maximum peak, the, they move from maximum peak with time, their maximum reduces to zero. And we'll be able to have this as a sketch so that we're able to understand what it is. So when you look at this, the peak of the oscillations reduces with the time, and this tells us about what are referred to as damped oscillations. So these are oscillations whose amplitude reduces. These are oscillations whose amplitude reduces with time due to lack of regeneration in the circuit. This, whatever I'm referred to as regeneration, is circuits that are able to create more energy so that we proceed, we continue with we have the oscillations maintained with the amplitude, or they grow with time. But because we lack these, we end up having whatever I refer to as a dying amplitude or dying oscillations. And that's why we are at this point towards as time increases, this oscillation will cease totally to be zero. So this explains what referred to as a damped oscillation. So another type that we're going to discuss is undamped oscillation. Lost during operation. So having known this, then we shall be able to know the effect on what affects oscillation. So another thing, we need the frequency of oscillation then. So from the circuit that we have seen is that the frequency of oscillation may be determined by two factors: the inductance of the inductor, and the capacitance of the capacitor. So the frequency oscillation, the frequency of oscillation is basically determined from two components, basically determined from the values of two components, i.e. the inductance of the inductor and the capacitance of the capacitor. Therefore, frequency is given by frequency of oscillations given by 1 over 2 pi. This is the formula for having the frequency, and this must be in what? Hertz.
So factors determine the stability. The stability of an oscillator. Number one is the operating point, what I refer to as the Q point. This is the chosen point for operation of the active device, and is such that it must not lie on the linear. It must not lie. It must not lie on the linear region. So another thing we need to have here is the circuit component. So these are the values of the capacitor and inductor, the values of the capacitance and inductance, the value of the capacitor and inductor. And the capacitor and inductor will directly determine the oscillation frequency. Number three is the supply voltage. The supply voltage. If the supply voltage is unstable, then the oscillation frequency will keep on varying. They keep on varying due to changes at different amplitudes. Changes at different amplitudes of the oscillations. Due to changes at different amplitudes of the oscillation. Another number four we shall have here is the output load. Output load. The output load, it affects actually during the loading, it varies. During loading, the energy
drawn by the load affect the operating point hence affecting the stability of the oscillator. Therefore, a buffer amplifier, is normally used. And finally, what I refer to as intermodulation during the operation. 5 is intermodulation. Intermodulation or intermittent. It should be intermittent. Intermittent capacitances. These are the differences and the changes. These are the differences and the changes that occur in capacitances and inductances. During operation. So we're going to know to conditions for oscillations, then we're able to do something else also. So the condition for oscillation are normally referred to as Bach-Hussein criterion. Bach-Hussein criterion. So this describes the necessary conditions for oscillations. They include, number one, the gain of the amplifier must be greater or equal to unity. So in other words, the gain must be greater or equal to unity. Number two, the net phase shift around the net phase shift. The net phase shift around the loop must be greater or equal to, must be zero or equal to 360 degrees. So from here we shall go through the types of oscillators. Basically, oscillators are divided into two depending on their output waveform. Roman 1 is sinusoidal. Roman 2 is sinusoidal oscillators. They are generally known as tuned oscillators. They include Roman 1, tuned collector oscillator. So we are going to have the diagram. So this is the tuned collector oscillator diagram, and from this you can see there's L1 inductor 1 in the primary and inductor 2 in the secondary. So L1 is a small winding so that it's able to capture a small feedback all the way back to the transformer. And because we must have a phase shift of 360 degrees, then 180 degrees is provided by the amplifier, which is the transistor, and another one by the inductor. So that we are able to have this. This whatever we are seeing here as an M is a mutual inductance between the two that coexist, so that when the current flows through the one, the electric field established there is coupled to the other inductor so that we are able to provide the feedback. That's why we talk of the mutual inductance, because there's no electrical connectivity between the two circuits, though they're able to link one another through the existence of the electric field around them. So that's the talk of mutual inductance. Then when we look at this circuit, is that whatever determines the frequency of oscillations are basically the L2 and C that we have there. And that's what makes us time the relationship between the output frequency of the oscillator. But also you must take note that for us to have the feedback factor, the feedback factor is determined by the ratio of the two inductances L1 and L2, so that we are able to know this. So whatever we need to understand is how does this circuit operate. So this is what we're going to learn. So the first thing is that when the circuit is energized, when this circuit is energized by providing the positive supply, then we shall be able to have the circuit, this one causing the circuit to bias here, and this one will be active. So when current flows here, this current will be creating an electric field that we shall have, the energy will be coupled to this and recharge the capacitor here. So by that, then at the end of the process, we shall be having an oscillation between the L2 and C1 that's taken back. So
when this oscillation starts, for us to get the 180 phase shift that remains other than the one that provided by the transistor, then we have to link these two through the mutual inductive effect. And that's what we need to know concerning this. So we are going to just describe it briefly so that we know what's going to happen. So whatever happens is that at the end of this, we shall be having a smooth oscillation. So if you are asked the output will appear to be like this. This is how the output is attuned, because this is an inductive and LC. These are the output waveform of the tuned collector circuit. So let us have a brief description of this. When the circuit is connected to power, when the circuit is connected to a power supply, the collector current starts increasing the current, the quiescent value. The collector current starts increasing towards quiescent value. Towards the quiescent value. And this current changes the capacitor, and this current charges the capacitor, and this current charges the capacitor, which then discharges through the inductor L2, charges the capacitor, which then discharges through the inductor L2. As I say, through the inductor L2. So another statement we need to do this. So when this charges through the L2, then we shall have an oscillation that's generated between the L2 and C1. So this results in oscillations and the coupling to the base of the transistor. The coupling to the base of the transistor is done through L1. Is done through L1. Once the capacitor is fully charged, once the capacitor is fully discharged, not charged, it's fully discharged. Once the capacitor is fully charged, it discharges. Oh, it's fully discharged. Oh, sorry that. Once the capacitor is fully discharged, the magnetic field or the magnetic energy in the inductor collapses and the whole process reverses to produce oscillations in the opposite, to produce oscillation in the reverse direction. The frequency of oscillation is therefore given by the frequency of oscillation is therefore given by F0 1 over 2 pi LC. So we're going to go to another type of oscillator. This is Colpitt's oscillator. We're going to also to have the diagram for this. And this one uses two capacitors that are grounded in the output terminal. We shall be able to draw this. So this is a Colpitt oscillator, and the Colpitt oscillator has a unique feature in such that the circuit that's used to produce oscillation has two capacitors, C1 and C2. So the charging process is that when we connect the VCC here, we shall have this device charge to charge C1 and C2, and then they'll be able to discharge through the inductor L. So that's how this thing operates. The frequency of oscillation will be given by the combination of the two capacitors when they are connected in series. So when the circuit, the operation, we're now dealing with the operation. When the circuit is connected to the supply, capacitor C1 and C2 are charged. Capacitor C1 and C2 are charged, and this capacitor discharges through the inductor L. And this capacitors discharges through the inductor L. So the frequency of oscillation is given by where CT is the two capacitors connected in series, where CT is supposed to be given by C1, C2, or C1 plus C2. In other words, these capacitors appears to be connected in series. This capacitor appears to be connected in series because there's a ground in between them and they're connected in series. So the oscillation about capacitor C2 is amplified as a feedback. It's amplified as a feedback to produce 180 degrees phase shift. Into the phase shift through the transistor. While the other 180 degrees phase shift is provided by the tuned circuit. We're going to go to the third one, Hartley oscillator. So this is a Hartley oscillator. A Hartley oscillator has a unique feature is that it uses two inductors in its tuning circuit. And this is the tuning circuit around here. This is the tuning circuit that composed of this capacitor C and L1 and L2. So it has got two inductors in the tuning circuit, with the primary inductor being connected to the output. So it's nearly the same way. We also supply the voltage, and this is the coupling capacitor for the feedback. So this how. So once we connect the supply here, then the collector current that will be established here will produce oscillations. And these oscillations are kept going by the positive feedback that's connected through the capacitor CB. So operation. When the circuit is energized, collector current flows. And when this collector current flows, one of the things we are going to establish that it established the field. Collector current flows through the inductors, and therefore the oscillations are produced in the tuning circuit that comprises of inductor L1, L2, and C. The frequency of oscillations is given by where LT is the combination of two inductances, and these two inductances are connected in series, where LT is L1 plus plus L2. L1 plus L2 plus 2M. The output is coupled through the inductor L. Through the inductor L. Coupled through the inductor L. So that marks, we shall be able to continue from there. The next lesson, we still have some oscillators to do. And we still have the oscillators, some of the oscillators that we have done, and the sinusoidal oscillators, we still have some of them to continue the next lesson. So I hope we are going to meet in the next lesson to wind up this unit so that we stand well placed as far as our learning is to be continued. Another thing I'll also to follow up on uploaded notes so that you're able to get the information concerning some examples that we have as questions, are posted as questions, are part of the application that we are doing today. So,